Hey, folks. All right. So thinking about which planets make magnetic fields and why, and which planets do you not expect to make magnetic fields? The most important thing to remember with terrestrial planets is that magnetic fields come from geology, right? They're coming from the chemical and geologic processes in the planet. And so how does the Earth release gases trapped in its interior to replenish the atmosphere? Well, from volcanoes, right? When volcanoes erupt, they, besides lava, they also emit gases like water vapor, carbon dioxide, some other gases. But those are the two big important ones for our purposes generally. Are larger planets or smaller planets likely to have active geology for longer? Well, what do we mean when we say active geology? What kind of active geology are we talking about? We're talking about volcanoes and plate tectonics and convection, right? All of this is powered by the interior of the planet being molten magma, convecting, flowing, because when the magma convects, then it's able to erupt out of volcanoes. So the question here really is, are larger or smaller planets likely to stay hotter for longer? And in there, it's larger planets, right? Larger planets are more likely to have active geology because they stay hotter for longer. And it is larger planets. Right? Are larger planets or smaller planets more likely to have high enough gravity to hold on to an atmosphere? Well, again, the larger planets are larger because they're more mass, right? So they have higher masses. Larger planets have higher masses, and therefore they have stronger gravity to hold on to more atmosphere, right? And then it talks about the dynamo effect, the dynamo theory, and how planets make a magnetic field via the dynamo effect. And so which parts of the Earth are generating the dynamo when you think about the magnetic field on Earth and on other terrestrial planets? Which part of Earth's interior is made of conducting metals? Well, conducting materials. What material is conductive? It's going to be the metals, right? So the magnesium, silicon, they're not metals. They're not great at conducting electricity. Iron and nickel are, though. And so the more metallic parts of the Earth are going to be better at conducting electricity, and you need to conduct electricity in order to make a magnetic field. So the inner and the outer cores are made of more conducting material. What parts of Earth's interior are molten? Well, see here, the outer core and the mantle. And outer core. What part of the Earth's interior is responsible for the magnetic field? Well, remember that the interior needs to be molten in order for it to convect, because you need convection for the dynamo, and you need to conduct electricity for the dynamo. So which part of the Earth's interior is both conductive and molten and convecting? It's the outer core, right? The iron and nickel in the outer core is hot, it's liquid, it's convecting and flowing in those convection cells, and that's what's moving the electricity, the electric charges around to generate the magnetic field here on the Earth. If a planet has a solid interior, will it have active geology such as volcanoes and plate tectonics? No, because in order to have active geology, you need hot, molten, convecting magma. You need the interior of the planet to be flowing around in order for it to erupt out of volcanoes, and you need convection in the mantle, right? You need the flowing magma in the mantle in order to move the crust around for plate tectonics. So, no, because you need hot, molten, convecting magma you need hot, molten, convecting magma to drive that active geology. That's a G. I'm writing too fast, you know? The key to good handwriting is to slow down. All right, I should do that. All right. Evaluate the following planets for likely magnetic fields. Okay, right? A planet will have a magnetic field if it is liquid and conducting, a liquid conducting material on the inside, and if it's rapidly rotating, right? You need that churning and the movement of the electricity to make the magnetic field. So if the planet is hot, molten, convecting, and conducting electricity, and also if the planet is spinning fast, then you'll make your dynamo. So Mercury is covered in craters. Does that mean it has active geology? No. Because if it had active geology, then there'd be volcanoes erupting, and volcanoes would cover over those old craters. So, no active geology. But that means no hot, convecting magma interior. And it rotates once every 57 days. That is not very fast rotation, right? If it takes 2 months to rotate once, that is slow rotation. So if it's not convecting and not rotating fast, then it shouldn't have a strong magnetic field. And it doesn't have a strong magnetic field. Venus, covered in active volcanoes. It has a thick atmosphere full of carbon dioxide that got pumped out of those active volcanoes. So, yeah, it has a lot of hot, molten, convecting magma powering and coming out of these volcanoes. It definitely meets our first criteria. But it takes 242 days to rotate once. That's not very fast. So if it's not rotating fast, then you're not going to get the electricity, you're not going to get the electric charges moving very fast, and therefore you can't make much of a magnetic field. So you would predict that Venus doesn't have a strong magnetic field, and you'd be right, it doesn't. How about Mars? Mars has craters, dormant volcanoes, and a very thin atmosphere, right? Why are the volcanoes dormant? Why is Mars covered in craters? Why does it have such a thin atmosphere? Because it doesn't have active geology. Mars used to have active geology, right? It used to be volcanically active. But then Mars cooled off. And when Mars cooled off, the magma stopped convecting, the volcanoes went dormant, the atmosphere either rained out via the inorganic carbon cycle, or it got blown away by the solar wind. And that's why the atmosphere isn't there anymore. And because the volcanoes aren't erupting to replenish the atmosphere, all of this tells you no recent geologic activity on Mars. But it does rotate fairly fast, right? A day on Mars is 24 and a half hours. So a day on Mars is only half an hour longer than a day on Earth. So that meets it. But still, you need both criteria. You need convection and fast rotation. Without the convection, there's nothing moving around very fast to make the magnetic field. The moon's covered in craters. There hasn't been active geology on the moon for a very long time. And also, it takes a month to rotate once, so the moon doesn't make its own magnetic field. The moon is inside of Earth's magnetic field, so the moon is protected a little bit from the Earth's magnetic field, but not much. Being on the moon, you're still subject to particles from the solar wind. So, there you have it. Right? Compared to the Earth, none of the other terrestrial planets, none of them have the ingredients for a dynamo. none of the terrestrial worlds has both hot convecting geology and rapid rotation to make a strong enough magnetic field. And the planet needs a strong magnetic field to protect it from the solar wind, from radiation. So maybe that's why we're here. Maybe that's why we live, why life evolved on Earth and not on one of these other planets, because we didn't have all the ingredients. Or the other planets didn't have all the ingredients. Earth is the only planet that had all the ingredients for a magnetic field, because living on a planet that's protected from radiation certainly makes life here on Earth a lot more pleasant and sustainable. Jupiter has the strongest magnetic field of any planet in the solar system. Which layer of Jupiter's interior is the liquid conducting material? It's the metallic hydrogen. Remember, metallic hydrogen is not solid, right? Thinking metal, it's not solid like a metal. It's metallic in that it conducts electricity. The metallic hydrogen is still liquid, like the liquid hydrogen layer. It's just such a dense liquid that electricity can easily flow from atom to atom to atom to atom, and it can carry electricity very well. So it's the metallic hydrogen. That's what makes the magnetic field in a Jovian planet. Ice giants don't have metallic hydrogen, but when water ice is mixed with other things like salts, ions, ammonia, other stuff, it can conduct electricity. So we need, for the ice giants to make a magnetic field, it can't be the rocky interior. It's got to be the water mixed with other impurities that can carry the electricity. Liquid hydrogen doesn't conduct electricity. Gaseous hydrogen, no. It's got to be the water and ammonia layer. That's what's able to convect, flow, and carry electricity in order to make the magnetic fields for Uranus and Neptune. All right. So let's think about these like fictional planets, right? Let's imagine we're looking for some alien worlds. Well, we are. Which ones would we predict would have strong magnetic fields? This first one here, okay, with a density of 5.4, what type of planet is that? That's got to be terrestrial. That's a terrestrial planet. So with a terrestrial planet, in a terrestrial planet, the layer that makes the magnetic field is the outer core, right? Molten, hot, convecting magma. And so does this planet have active, flowing, hot magma? Well, it's got active volcanoes. It's got a thick atmosphere. Sure looks like it must have, I mean, if there's active volcanoes and a thick atmosphere being made by the volcanoes, then the planet must have a hot, convecting magma interior. So that meets our first criteria. It rotates once in 150 days. It takes 150 days just to rotate once. That's pretty slow. So it doesn't meet both of our criteria. This one probably doesn't make a strong magnetic field. Why? Why doesn't it make a magnetic field? Because it has slow rotation. How about our second one? A density of 6.8, also terrestrial. What do you find on the surface? Craters. Craters mean old, right? Craters mean the planet must be old, geologically dead, not convecting. So it can't have, if it doesn't have convecting magma, it can't make a dynamo. It can't make a magnetic field. It does rotate fast though, right? One rotation in 10.5 hours, that's fast rotation, but you need both criteria to make your dynamo. So it can't be making a magnetic field because there's no magma convection to move those charges around and make your magnetic field. How about this one here? Okay, a density of 1.6. That is what kind of planet? That is an ice giant. So what makes the magnetic field in an ice giant? It's the water ammonia layer. So, what do you find on this planet? Well, it has storms and clouds made of water and ammonia, so that seems to match what we like. And it's rotating once in 9.5 hours. That's pretty fast. So, yeah, I'd say that has everything we need, right? It's got fast rotation, and water and ammonia. Ammonia is NH3. So it's got everything we think we need for an ice giant to make that magnetic field, to make the dynamo. How about this density? With a low density like that, that's got to be a gas giant. In a gas giant, what makes the magnetic field? It's the metallic hydrogen. So it's got storms, it's got belt, it's got zones, it's got everything that Jupiter and Saturn have. Do we know for a fact that it's got metallic hydrogen? Well, you can't see the metallic hydrogen layer, right? The metallic hydrogen layer is buried way down here, and if you're looking at the planet, all you can see is the cloud tops, right? But Jupiter and Saturn both have metallic hydrogen. They're both gas giants. Jupiter and Saturn both have a strong magnetic field. This gas giant has storms and belts and zones and everything that it looks like Jupiter and Saturn have. So, probably, yes. Is it rotating fast? Well, it rotates in 8 hours, so spinning once in 8 hours is pretty good. So, yeah, this one probably also has a magnetic field because it's a gas giant. How about this density here? A density of 5.3, that's another terrestrial. It's a terrestrial that has active volcanoes, a thick atmosphere, plate tectonics. Great. Active geology means it's hot and convecting on the inside. It's got magma. It's rotating in 21 hours, which is just a little bit faster than Earth. So sure, it's got everything that we think a terrestrial planet needs to make a magnetic field. So we're going to say yes. It's probably got a magnetic field because it's a lot like Earth. 4.2, also terrestrial, covered in craters. So it's old. It's got an old surface, no active geology, no convection on the inside, and it's rotating in 50 days. That's way too slow. So it probably doesn't have a magnetic field. Right? It fails on both counts. This last one here, density of 3.1, and it's got ice ridges, it's got volcanoes. This one's a little tricky because we don't know if the volcanoes are active or dormant. Right? You take a picture of this planet and you say, hey, look, there's a volcano, but we're not seeing it erupt, but we're also not seeing it be dormant, like on Mars. So, But it's got ice ridges. Which means what? Well, if it's got giant mountains of ice, they're probably dead volcanoes, right? Because if volcanoes are active, they are pouring out lava. And when lava pours across the surface, that lava is going to melt that ice, and you're probably not going to have a lot of buildup of ice on a planet that's regularly getting lava poured on it, melting the ice. So this one's a little tricky, right? It doesn't say anything about an atmosphere. Does it have an atmosphere? We don't know. If it does, apparently it's not enough for us to report on. Probably not. Seems like a bad bet, right? Probably the volcanoes are dormant. That's how, the volcanoes are dormant, so there's no new gas being pumped into the atmosphere, which is why we can't see a thick atmosphere like we're reporting over here. A lot of buildup of ice, which is going to mean the planet is cold on the outside and the inside, probably. Seems like a good bet to say probably not geologically active. But it's rotating in 18 hours, so that's fast enough, I suppose. Still, nah, probably not, right? But we made this one last for a reason, right? This is a little bit tricky, right? It's got a density of a low density for a terrestrial object, right? A density more than 1 means it's terrestrial, but it's really close to the density of rock, right? A planet of pure rock has a density of 3, so this is only a little bit more dense than this. And it's got a lot of ice, so it's probably a planet with a lot of ice and a lot of rock and some metal. This is like Pluto, right? This really is a planet like Pluto. Low density, ice ridges. We found evidence of old volcanoes on Pluto, probably dormant. Pluto rotates even faster. Pluto rotates in like 6 hours, but still doesn't make a magnetic field. So some of these planets we know enough to make a pretty good determination of saying, like, yes, it does, no, it doesn't. But hey, Pluto is way out there, far from the sun. It's at the outer edge of the solar system, and we don't know as much about Pluto as we know about the other planets. So you got to go with your best conclusion, and the best conclusion is this planet. If this planet is like Pluto, then it probably doesn't make a magnetic field because Pluto doesn't either. All right. Hopefully that makes some sense, and post your questions if you've got them. Otherwise, have a good day.